Hi, welcome to another lecture of MATH336. So now we're moving on to chapter 4, and chapter 4 is about solving initial value problems using Laplace transforms. So this is the table of Laplace transforms, and this is to be found at the front cover of your textbook. So if you open your text, my textbook's kind of broken here, but so here's the textbook, and if you open the front cover, right there, you see the table of Laplace transforms on the left, and on the right, there's a table of integrals. So this will become a very valuable table. So we're going to learn how to use this table of Laplace transforms to solve initial value problems. So for now, I won't go through this in detail, but in this lecture, I want to highlight a few of these properties that we're going to use today to solve some initial value problems. Okay, so we're all going to become very familiar with this table. Now, the textbook actually starts out with section 4.1 with, defining what is the Laplace transform. This is what it is. So the Laplace transform of a function f of t is equal to this integral. Okay, so that's how they start the story about Laplace transforms. However, I think it's better to see what Laplace transforms are used for first. And we don't need to understand this definition in order to use Laplace transforms to solve initial value problems. We just need that table of Laplace transforms. So before we study this formal definition of the Laplace transform in section 4.1, let's see how we can use the table of Laplace transforms, which is given above in these notes and in the front cover of your textbook, to solve initial value problems like the ones in chapter 2. So what is the process for using Laplace transforms to solve an initial value problem? So it's this is the diagram where I'm sort of dividing the top and the bottom here. The top is the time domain, t, and the bottom is the Laplace domain, which uses the variable s. Okay, so we have an initial value problem in the time domain, and it's about finding this function x of t. Okay, so it's a differential equation with some initial conditions. We apply the Laplace transform to the differential equation, and this will produce an algebraic equation in the Laplace transform of the function. Then we take this algebraic equation and we simply solve it algebraically. So we will have, this term appearing in a few different places in the equation, and we'll solve for it. So we'll find out the Laplace transform of x of t is equal to, something. Then finally, we do what's called the inverse Laplace transform, and that will take us back to the time domain where we recover now the solution of the initial value problem. Okay, so that's the process that we're going to be looking at in this chapter. So let's get started with this, and I think today we'll just do a few examples of this so we understand how it works, and we'll start with simple examples, and then in future sections we'll look at more complicated examples that use more properties of the Laplace transform. But for now, let's look at the following properties. So I'm just going to look at these 9 properties from the table of Laplace transforms. The first property, it's not really a property, it just says that when we write capital F of S, that is the Laplace transform of lowercase f of t. Okay, so that's all that is. So, so just keep that in mind when we're going through this. So the first property that's actually a property is this one. It says that if you take the Laplace transform of the derivative of f of t, then this is equal to s times the Laplace transform of the function f, and then minus the value of f at 0. Okay, so that's what we get. And I mentioned this before, that it's very interesting with Laplace transforms. If you want to take a derivative, in some sense, this corresponds to multiplying by s. So we're doing s times the Laplace transform of the function. So differentiation corresponds to multiplying by s. And you can see this again here. If we took the Laplace transform of the second derivative, it corresponds to multiplying the f of s by s twice. So we multiply by s squared, and that gives us that sort of equivalent in the Laplace domain. Multiplying by s twice corresponds to taking the derivative twice in the time domain. Okay, so it's not precisely that, because there's also these terms that we need to subtract off. So it's multiply by s twice, and then subtract s times the value of f at 0 minus the value of f at f, the value of f prime at 0. Okay, and this is why these Laplace transforms are especially useful for solving initial value problems, because with an initial value problem, we are given values for the function at time 0, and we're given values for the derivative of the function at time 0. Okay, so that's where the initial values will go in. They'll go into, we'll plug them into these guys right here. Okay, so I haven't actually given you a Laplace transform of anything yet. So here's the first function that we'll look at the Laplace transform of. So what is the Laplace transform of the function that's just 1? And it turns out the Laplace transform is 1 over s. Okay, what is the Laplace transform of the next simplest function? T. So the Laplace transform of that corresponds to 1 divided by s squared. And you can actually check, I mean, based on what we know, what do you get when you take the derivative of t? You get 1. And how do we go from 1 over s squared to 1 over s? We multiply by s, right? So there's that idea again. Differentiation in the time domain corresponds to multiplying by s in the Laplace domain. Okay, obviously this is a very important function for us in differential equations, and the Laplace transform of this function is going to be 1 over s minus a. And I suppose it's a good idea to check that if a is 0, then this is going to be equal to 1. And we get 1 over s minus 0, which gives us 1 over s. So we see that those things match. Okay, what's the next function? So it's actually these two come together. So the Laplace transform. So these are the other very important functions in differential equations: sine of kt and cosine of kt. So the cosine of kt is given by this term, and sine of kt is given by this. And you notice the difference is the cosine has the variable s in the numerator, and the Laplace transform of sine kt has the constant k in the numerator, but the denominators are the same. So it's easy to confuse these two, but yeah, somehow remember that cosine has s in the numerator and sine has k in the numerator. Okay, and finally, one more property, a very important property that makes everything work, is that the Laplace transform is actually a linear operator. So just like differentiation or integration, if you were to take like the derivative of, a times f of t plus b times g of t, it would be a times f prime plus b times g prime. And that's because differentiation is a linear operator. And the Laplace transform works exactly the same way. So when you have the Laplace transform of a linear combination of two functions, then it's simply a times the Laplace transform of f plus b times the Laplace transform of g. So we can distribute the Laplace transform across the sum, and we can factor out the constants in front of the functions. And one important thing to notice from this fact that it is linear is that if a and b are both 0, then we get 0 times this plus 0 times this, and so that gives us 0. So the Laplace transform of 0 is 0. Okay, so there's the sort of initial Laplace transforms that we're interested in, that we'll need for today. So what we'll do is examples that use each of these properties today. Okay, so let's start with this first example. Now, I think maybe in order for us to really understand what's going on, maybe we should solve this differential equation using the chapter 2 techniques of using the characteristic equation. And then we'll have the answer. And then we'll do the same thing with the Laplace transforms. And that will, then we can compare, which of these two methods do we prefer? Which one was easier? So let's give this a shot. So let's see. So first of all, let's do it using the, we'll use, so first we will use the chapter 2 technique. Okay, so first let's use the chapter 2 technique. Okay, so what is the chapter 2 technique? It says we write down the characteristic equation and we solve it. Here we get plus or minus 3i, and that gives us our general solution. Um, 3t, oh, x. So now we're doing x. So x is this. Okay, and then we need to use our initial conditions in order to determine the value of those constants. So take the derivative. So this step of taking derivatives, we're going to be able to avoid this step when we're using Laplace transforms. Okay, so x of 0 equals 3 and x prime of 0 equals 4. So we have c1 times 1 plus c2 times 0 is equal to 3. And we have minus 3c1 times 0 and then plus 3c2 times 1. So we get that c1 is equal to 3 and c2 is equal to 4 over 3. And so therefore, the solution is 3 cosine 3t plus 4/3 sine 3t. Okay, so now we have the solution, so let's use Laplace transforms to do the same thing. So now we will solve the initial value problem using Laplace transforms. Okay, so how do we do this? So we take our differential equation, here's the differential equation. And what we're going to do is we're going to take the Laplace transform of both sides. So we'll do the Laplace transform of the left side, and we'll do the Laplace transform of the right side. Now, because the Laplace transform is linear, we can distribute the Laplace transform across the sum, and we can factor out any constants. And we know the right-hand side, the Laplace transform of 0 is 0. Okay. All right. So what is the Laplace transform of the derivative, x double prime? So I'm going to use capital X of s, and that will be the Laplace transform of little x of t. So that's the convention, uppercase letters for the Laplace transforms. So according to our second derivative rule from the table, we will have s squared, capital S, capital X of s, minus s times x of 0, minus x prime of 0. Okay, so that's the first term. So maybe I'll put parentheses around that, or some brackets. And then we have 9 times x of s, and that is equal to 0. Okay, so now let's plug in the values that we know for these x of 0 and x prime of 0. So this will be 3 and 4. So we're going to get s squared. I'm going to combine these terms together, first of all. So collect the x of s terms together, and then 3 and 4. So this will be minus 3s minus 4 equals 0. Okay, so now we will solve this for x of s, and we get 3s plus 4 over s squared plus 9. Okay, so there's our final Laplace transform. And in order to do the inverse Laplace transform, we will need to break this apart into two pieces. Because from the properties I mentioned before, there's no inverse Laplace transform of precisely this expression here. So how do we break this apart? So we're going to do 3 times s over s squared plus 9. And if you recall, this is the Laplace transform of cosine 3t. So there's cosine 3t right there. And then on the other side, we have plus 4 times 1 over s squared plus 9. Now remember, this is kind of like sine of t, but because there's a 9 down here, we actually need a 3 up here. But that's easy to fix. We just put a 3 there, and then we divide by 3 here. And you should see very quickly that we're getting precisely the C1 and C2 values that we were getting from before. I'm sorry, my dog wants to get out of this room, so 1 second. Okay, so she's probably going to scratch on the door to come back in again. But for now, she's hopefully happy out there. Okay, so now we'll do the inverse Laplace transform. So we're going to have the inverse Laplace transform of both sides. So the inverse Laplace transform of x of s is equal to the inverse Laplace transform of the right-hand side. Now, I'm going to write this out in a lot of detail, but in the future, we'll be able to just skip some of these lines that I'm writing down. So the inverse Laplace transform. And I don't know if it's in the table or not, but the inverse Laplace transform is also linear. So yeah, I mean, I think that sort of comes through from the fact that the Laplace transform itself is linear. So on the left-hand side, what is the inverse Laplace transform of capital S, x of s? We get x of t. And on the left-hand side, on the right-hand side, we will distribute the inverse Laplace transform and factor out the constants. So maybe I'll put a dot there to indicate multiplication. And then we know that the inverse Laplace transform of s over s squared plus 9 is cosine 3t. And we know that the inverse Laplace transform of 3 over s squared plus 9, that is sine 3t. So you see we get precisely the same answer. I did not say Siri. Siri, go away. Okay. Okay. So there you have it. So that's the first question down. So I mean, some of these steps can be skipped, of course. Essentially, we're not going to actually write this down anymore, and probably won't write this down either. We'll just immediately go from the differential equation directly to this line. Okay, so we'll do that. And then, usually there's some, rearranging and stuff. And then finally, we solve for x of s. And then we do need to do this kind of process where we break it apart into things that we know how to invert the Laplace transform of. But then typically we just go from this line, directly to this line. So this was just like in between stuff to explain, but normally we wouldn't write that stuff down. So it may look like it's a bit longer than what we did above. This definitely seems quite compact, but in fact, we can make this very much compact as well. So let's do some more examples and we'll see how this works. So where's my next example? Okay, number 4. Okay, so again, maybe let's do it both ways, right? So let's start by doing it the chapter 2 way. Of course, you may prefer chapter 2 at this point because that's what you're familiar with. But I hope you'll realize you'll grow fond of this Laplace transform method. It's quite amazing the way it works. Okay, so there are the roots, and therefore our solution is going to be C1 e to the minus 3t plus C2 e to the minus 5t. And we take the derivative. Okay, just kind of squeeze it in there. Okay. Now we use our initial conditions. Oh, I keep using y. I'm so used to using y here, but it's actually typically use x in this chapter. So x of 0 is 2. So we get C1 plus C2 is equal to 2. And x prime of 0 equals minus 3. And we get minus 3 C1 minus 5 C2 equals minus 3. Now we need to solve this linear system. So let's use Cramer's rule. So I'm not going to write down Cramer's rule, but I think we're all familiar with Cramer's rule now. So we get this. Okay. Oh, maybe I'll do that below. And C2 is this. So we put the right-hand side in the second column. So C1 is equal to minus 10 plus 3. And the denominator is minus 5 plus 3. So we get C1 is equal to minus 7 over minus 2, which is 7 over 2. Okay, now the C2 term, it's going to be minus 3 plus 6 over minus 2, because I know that that's minus 2. So I get C2 is equal to 3 over minus 2, or minus 3 over 2. Okay, so therefore, the solution is going to be 7 over 2 e to the minus 3t minus 3 over 2 e to the minus 5t. So there's our solution. Okay, so now let's do the same thing, but with Laplace transforms. Okay, so what is our differential equation? Here it is. I'll just copy this, put that there, so for reference. Okay, so now we're going to take the Laplace transform of both sides of this differential equation. The x double prime, that becomes s squared x of s minus s times x of 0 minus x prime of 0. Now, I guess I could write those values in directly, but I just want to make sure everyone understands what's going on. Okay, and now it's going to be plus plus 8 times the Laplace transform of x prime, which is s times x of s minus s, sorry, no, it's not s, so minus x of 0, and then plus 15, and this is just the Laplace transform of x of t, and the right-hand side is 0. Okay, so now let's plug in our initial conditions and rearrange everything. So we have s squared plus 8s plus 15 times x of s. And then we have minus 2s plus 3, and then minus 8 times 2, so minus 16, and that is equal to 0. Okay, and now we'll solve for x of s, and we're going to get 2s minus 13, oh, plus 13, almost made a mistake there, plus 13 divided by s squared plus 8s plus 15. Okay, and maybe I'll put a box around that. So there's the Laplace transform of our solution. Okay, now we need to do the inverse Laplace transform. And to do that, we need to break this expression up into pieces that we know how to invert. Okay, and if you're sort of paying attention, you'll notice that this this numerator here, that's actually precisely this characteristic equation here. So, and that's not a coincidence. So that's always going to be the case. So we're sort of getting like the characteristic polynomial down here in the denominator. So in order to break this up, we actually still need to factor this. So that's not something that we can avoid, but we're definitely avoiding taking derivatives and solving for C1 and C2. So that part we're going to avoid. And that's usually the part that's not so much fun when solving differential equations using chapter 2 methods. Okay, so what do we do? So let's factor the denominator. And we're going to get, so we already know, we factored it above, so it's s plus 3 times s plus 5. Okay, now what we want to do is write this as some number a over s plus 3 plus some number b over s plus 5. So what we're doing here is partial fractions. So you may remember this technique from probably Calculus 2, I think, where you learn how to use partial fractions, the technique of partial fractions in order to integrate things like this, right? So if you're trying to integrate something like this, you would need to use partial fractions in order to integrate it. So we're doing partial fractions in order to take the inverse Laplace transform. Okay, so what's the technique of partial fractions? What I'm going to do is I'm going to take this equation here, and I'm going to multiply both sides by this denominator, and that will get rid of it, so there won't be any fractions anymore once I do that. So multiplying both sides by the denominator, I get 2s plus 13 on the left, and on the right, when I multiply this term by the denominator, this and this will cancel, and we're just going to be left with s plus 5. So we'll have a times s plus 5, and then when we multiply this guy by this denominator, the s plus 5 and s plus 5 will cancel. So we'll just have the s plus 3. So b times s plus 3. Okay. So there are different ways to solve for a and b with these things. We could, multiply this out and collect the s terms together. So we'll get a plus b is equal to 2, and we'll get 5a plus 3b is equal to 13. But now we're solving like a 2x2 linear system, 2 equations and 2 unknowns, like we did before. And there's actually an easier way to do this here. Instead, we'll see that a very useful technique for determining a and b is to substitute certain values of s into this equation, because this is an equation that's true for all s. So I can substitute certain values of s in here so that certain terms will disappear. For example, if I put s equals minus 3, then minus 3 plus 3 is 0, and so this term will disappear. And that will let us solve for a. So let's do that. So s equals minus 3. And what do we get? We get minus 6 plus 13 is equal to 2 times a. Yeah, that's it. It actually looks like Cramer's rule, doesn't it? Because we get, this is precisely the thing that we had in the numerator. Well, maybe we had the negation of that. What did we have for Cramer's rule? We had, oh, maybe it's different. I'm not sure. So maybe I was thinking of this, minus 3 plus 6. I don't know. I guess it's a little bit different. Anyway, we'll see what we get. So we get 7 on this side, 7 divided by 2. So it's 7 over 2. So that's the C1 coefficient that we were looking for. So it's actually this one here. Okay. 7 over 2. And then we substitute s equals minus 5 in order to make this guy equal 0. And what do we get? We get minus 10 plus 13 is equal to minus 2b. And so b is equal to 3 divided by minus 2. So we get minus 3 over 2. And if you recall, that's the value of C2 above. Okay, so now we have it. So therefore, x of s is equal to 7 over 2 times 1 over s plus 3 minus 3 over 2 times 1 over s plus 5. Did I do it the right way? Yes. And so therefore, we take the inverse Laplace transform of both sides. We get 7 over 2 times the inverse Laplace transform of 1 over s plus 3. And if you look at your table, remember that the Laplace transform of e to the at is 1 over s minus a. Right? So remember, it's s minus a. So here, we would actually have e to the minus 3t. Right? So if I took the Laplace transform of this, then I would get 1 over s minus 3, which would be this, 1 over s plus 3. And the same thing goes on the other side. We would have e to the minus 5t, because taking the Laplace transform of this gives you precisely this. So you have to be a little bit careful with the signs there to make sure that you've got everything the right way. And there's exactly the same solution that we got doing it the other way. All right. Let's do another one. Okay. Let's see. So let's again do it both ways. Now this one is interesting because it's a non-homogeneous equation. So we're actually going to have to find a particular solution, and then we'll be able to solve it. So let's go ahead and do that. So the chapter 2 way, we have to first solve the homogeneous equation. So we get r plus 1, or maybe I'll do 3 first. R plus 3 times r plus 1 equals 0. So r is equal to minus 3 minus 1. And so the complementary solution is going to be C1 e to the minus 3t plus C2 e to the minus t. Okay, so there's our complementary solution. Now we need to find our particular solution. So we have the function on the right is equal to 1. And if I take the derivative, I just get 0. So clearly the phi function that we're choosing is just going to be 1. That's the only term that appears in f and its derivatives. So that's it. So the particular solution is going to be a times 1. So just a. So now we need to figure out what is the value of that a. And to do that, we need to take the derivative of it twice, I guess. So we get 0 both times. So then let's substitute that in. Oh, I'm using y again. I'm so used to using y. So in this case, these are x's. X. Okay. So we have x double prime p plus 4x prime p plus x 3x p is equal to 1. And we have 0 plus 0 plus 3 times a is equal to 1. And so therefore a is equal to 1/3. Okay, I'll just circle that. So there's the value of a. So therefore our solution is going to be our complementary solution, e to the minus 3t plus c2 e to the minus t plus 1/3. So there's our general solution for the differential equation. And now we use the initial values to determine the value of C1 and C2. We have 0 and 0. Okay, that should be pretty easy, I'm imagining. 0 and 0. Okay, so we have C1 times 1 plus C2 times 1 plus 1/3 equals 0. And we have, oh, I forgot to take the derivative. 1 second, move that down. X prime equals plus 0. Okay, so that's just that. Okay, now we're good to go. Minus 3c1 minus c2 is equal to 0. Okay, so we get this linear system. C1 plus C2 equals minus 1/3. I guess we could multiply both sides by 3 if you want. It might make things a little bit easier. So let's do that. So I'll do 3c1 plus 3c2 is equal to 1, and minus 3c1 minus c2 is equal to 0. Now, when I get something like this, where I can easily see that if I add those two equations together, then the C1 will cancel. So let's just do that instead of using Cramer's rule, because this is going to be easier. When things aren't so nice, that's when I like to use Cramer's rule instead of doing this. Okay, so we're going to have 0, and then 2c2 equals 1. And so c2 is equal to 1/2. And then let's substitute that in. So we know c1 plus c2 equals negative 1/3. Oh, I almost made a mistake. Negative, right? Negative 1/3. It's negative, negative. Okay. So now, let's see. c1 plus c2 equals negative 1/3. So I have c1 plus c2 equals negative 1/3. And so c1 is equal to 1/2 minus 1/3, which is 3 minus 2 over 6. And so c1 is equal to 1 over 6. Okay, and so therefore, the solution of the differential equation is 1 over 6 e to the negative 3t minus 1/2 e to the negative t plus 1/3. Okay, so this is going to be very interesting to see what happens when we use Laplace transforms to do this. How is it going to be different when we're using, when we're solving a non-homogeneous differential equation? Okay, so let's grab that differential equation, this initial value problem. So I'm going to copy this down here so you can have it for reference. And let's take the Laplace transform of both sides. So we're going to have s squared x of s minus s times x of 0 minus x prime of 0. Notice those are just going to be 0, so that's going to be nice. Plus 4 times s x of s minus x of 0. Oh, I'm running out of room here on this page. Instead of crowding it, I will just go to the next page. Maybe I'll just move this whole thing to the next page. Okay. And then, yeah, let me move this over here. And we'll have plus 3 times the Laplace transform of x of t. And then the Laplace transform of 1 is 1 over s. I believe. I'm just looking at the table. Yeah, there it is. Laplace transform of 1 is 1 over s. Okay. So all these guys are 0. So I'm not even going to write that stuff in. That's all 0. So I'm just going to get s squared plus 4s plus 3 x of s is equal to 1 over s. Okay, now we'll divide both sides by this guy, which you may recognize as the characteristic polynomial, which is always going to be the case. So we'll get 1 over, and then let me just factor this already. So s plus 3 times s plus 1. Okay, now we're going to do partial fractions. So the form that we're looking for is a over s plus b over s plus 3 plus c over s plus 1. Multiply both sides by the denominator, and we get 1 is equal to a times s plus 3 times s plus 1, because the s cancels. And we get plus b times s plus 1, because the s plus 3 cancels. And we get plus c times s plus 3, because the s plus 1 cancels. So there's our equation. And now we'll substitute things in. So let's first of all substitute something that lets us solve for a. If we put 0 in for s, then these terms will go away. So that's what we'll do. So let's do s equals 0. Get 1 equals 3 times 1. So we get 3a. So a is equal to 1/3. We recognize that 1/3 from solving it before. That was that turned out to be the particular solution. Now what do we do? So let's solve for b. So if we put s equals -3, then that will be 0. That will be 0. So those guys go away. We'll solve for b. So -3 to get 1 equals -3 times -2. So that is 6. And we get 1/6, which we recognize. And then we get, we'll put in -1 now. So -1 will get rid of the a and the b, and we'll just solve for the c. So we get, sorry, oh my God, my dog scared me. Jeez. All right, 1 second. It's like scratching at my door, like what's like in The Shining, here's Johnny. That's kind of what she does. Okay, 1 second. So I open the door and my dog is not even there. It's so scary. I look down the hall, she's not there. So it's like a ghost just scratched on my door. So very, very frightening. Okay. Where were we? -1 times 2. -2. C is -1/2. Okay, I think that's what we had from before. -1/2, 1/6, and 1/3. Yeah, -1/2, 1/6, and 1/3. Okay, so that's obviously, we see where we're going now. So that means that the Laplace transform is equal to 1/3 times 1/s plus 1/6 times 1/s plus 3 minus 1/2 times 1/s plus 1. Okay, and now we do the inverse Laplace transform. We get 1/3, and the inverse Laplace transform of 1/s is 1. So it's 1/3 times 1. Plus 1/6, inverse Laplace transform e to the -3t. And then the inverse Laplace transform of this is e to the -t. We get exactly the same solution. And I think it's easier. I do. I'm starting to believe, right? Look at what we, it was all just like basic algebra. There was really there was no derivatives. There was no solving equations. We simply got this algebraic equation. We solved it. We did partial fractions. Very easy to solve for these coefficients using the substitution technique. And we get our solution, right? And just look at how much space it took to do that, and how much space did it take to do this one, right? I had to write more, definitely had to write more. Had to take derivatives, had to solve a system of equations. Not fun. This is really cool. This is really, really cool. So I like this a lot. I hope you agree. This is in many ways, a much better way to solve these types of differential equations. Okay, let's do another example. I think this is the last example today. Yeah, so this is it. So this is the last example. Okay, so again, we'll solve it both ways. I think it's really interesting to see the comparison. So r squared plus 3r plus 2 equals 0. R plus 2 times r plus 1. So granted, these are very simple examples, right? So we're seeing like, the first one had sines and cosines, but these ones are just having like exponentials. Okay, so r is equal to -2 minus 1. And so the complementary solution is C1 e to the minus 2t plus C2 e to the minus t. There's our complementary solution. Now we have to find the particular solution. F of t is equal to t, and when we take the derivative, we get 1, and after that we get 0. So we have two terms that we need to include in our particular solution, t and 1, and those are both not solutions of the homogeneous equation, so we're good to go. So therefore, the particular solution has the form a t plus b. Okay, so there's the form of the particular solution, and we need to substitute that in to the differential equation. So let's take the derivative once, and then twice, and now we can substitute that in. So let's see, this will be x double prime p plus 3x p prime plus 2x p is equal to t. So we have 0 plus 3 times a plus 2 times at plus b is equal to t. Okay, so we get 2at plus 3a plus 2b equals t. Okay, so that means that 2a is equal to 1, and 3a plus 2b is equal to 0. So a is equal to 1 over 2, and that means that we get 3 over 2 plus 2b equals 0, and that gives us b is equal to -3 over 4. Okay, so therefore, the particular solution is 1/2 t minus 3 over 4. So now let's write down our general solution. C1, I already forget. E to the -2t, okay, -2, -1. -2t plus C2 e to the -t, and then our particular solution okay. Now we use our initial conditions to find the C1 and the C2. Notice that the Laplace transform method, the Laplace transform method is almost like doing the opposite thing. So with this method, we use the initial conditions at the end to find C1 and C2. With the Laplace transform method, we're using the initial conditions at the beginning. And with this method, we find out these terms, immediately at the beginning. But with the Laplace transform, it's only at the very end that we determine what those functions are that go there. So it's kind of like doing things in a different order. We're doing all the same things, but we're doing them in a different order. Okay, so I need to take the derivative of this. Let's see if I can squeeze it in here. Okay. And now what are the initial conditions? 0 and 2. All right, I'm gonna multiply to get rid of these fractions. So, so the first equation becomes 4c1 plus 4c2 equals 3. And the second equation becomes negative 4c1 minus 2c2. And then this will become 1, and that will become 4. So it'll be 4 minus 1, which is 3. Okay, so again, I see this is quite nice to solve. Just add these together, and I'll get 2c2 is equal to 6. And so we get that c2 is equal to 3. And then we have c1 plus c2, which is 3, is equal to 3 over 4. And maybe it's might be easier to just use that other equation. Let me just use this one here. So what would we get? We get 4c1 plus 4 times 3 equals 3. So c1 is equal to, so we get 3 minus 12, which is minus 9. So we get minus 9 over 4. Okay, that was easier. So therefore, the solution is minus 9 over 4. E to the what? E to the negative 2t. Plus 3 e to the negative t, was it? Yeah, negative t. Yeah. And then we have our particular solution. 1/2 t minus 3 over 4. All right. Let's use the new technique now. Okay, that was quite long. Let's see if we can do it with less work. So now using Laplace transforms, the Laplace transform of x double prime is s squared, x of s, minus s times x of 0, minus x prime of 0, plus 3 times s of times x of s, minus x of 0, plus 2 times x of s, and then the Laplace transform of t is 1 over s squared. Okay. Combining stuff together, there's that characteristic polynomial that we expect to see. Right? See that? So there's the equation, and we get exactly the same thing showing up there. And now we have, so this will be 0, that's 0. So we just have this term. So that is minus 2 equals 1 over s squared. Okay, So x of s is equal to 1 over s squared. And then I'm going to factor this. We know the factors. It's s plus 2 times s plus 1. So there's that term. And then we're going to move this minus 2 over here. So that will be a plus 2 over s plus 2 times s plus 1. Oh, my dog is scratching on the door, but she was more gentle about it that time. All right, I'll just keep recording. There you are. Hello. Okay, well, so now that I think of this, maybe what I should have done is combine these two terms together initially. So really, it would have been better to just add this over here first and then divide by this. So what would we have gotten in that case? So we would have had, so we're doing like, imagine we're doing like, plus 2 here. So that's really going to be plus 2 s squared over s squared. So we get 1 plus s squared, 2s squared in the numerator. So that's what we'll get here, 1 plus 2s squared. So hopefully that was easy to follow. And now we want to do partial fractions. So we get a over s. And if you remember, so we're going to go over this in more detail, but if you remember partial fractions, when you have an s squared term like this, you need to do an s term and then an s squared term. So if this was like s cubed, then you would need s squared, and s cubed, like that. So you need all of them in order for the partial fractions to work. Okay, so that's just a reminder of how partial fractions works. And then the other terms just appear once, so we just get c over s plus 2 and d over s plus 1. Okay, now we'll multiply both sides by the denominator. We'll get a times s plus 2 times s plus 1 plus b times s plus 2 times s plus 1 plus c s squared times s plus 1 plus d times s squared times s plus 2. Okay, so hopefully you followed that. I'm just canceling things that cancel, and we get this. Okay, so now we have to think, I think this is going to be a little bit trickier to substitute stuff in, but let's see if we can figure this out. Let me see. So first of all, what would we substitute in so that we have, so we get a, but all the other terms disappear? Well, I guess it's not so clear, so we could get rid of this by substituting in -2 or -1, but then that will disappear. This one we could do 0 or -1, but then that will disappear. And then here this will be 0 or -2, and again the a disappears. So maybe let's return to the a in a bit. Yeah, let's return to the a. Just trying to think. Yeah, we'll come back to that one. Let's come back to the a. So let's do the other terms first. So we'll do the let's do 0 first, and that will let us solve for b. So we get 1 is equal to 2b, and then that gives us, let's see, that will give us b is equal to 1 over 2. Okay, so we got b. And now if we do s plus, make s plus 2 equal 0, then we'll solve for c. So these terms will all disappear. So we'll do s equals minus 2. And we get 1 plus 2 times 4, which is 9. And we'll get 4 times negative 1. So negative 4c. So c is equal to negative 9 over 4. And then s equals minus 1. We get 1 plus 2 is 3. And let's see. That'll be 1 times negative 1 times 1. 1 times 1. So d is equal to 3. Okay. Now what about a? What about a? So one way to get a is to notice that a is going to be the coefficient of s cubed here. And then there's another s cubed here, so it's c times s cubed, and there's another s cubed here as well, so d times s cubed. So looking at the coefficients of the s cubed, so coefficients of s cubed, and this will give us, on the left, there's no s cubed, so it's 0. On the right, the coefficient of the first term is a, and then we get plus c plus d. And now we can solve for a. Okay. Yeah, I'm thinking there's other ways of doing this as well. I think that's a nice way to do it. I think another way I'm recalling is to take the derivative of both sides of this, but we're doing Laplace transforms. It'd be nice if we could just avoid taking derivatives. That's one of the nice things about Laplace transforms is you don't need to take these horrendous derivatives and solve these terrible linear systems. So let's think of it this way. I think this is a good way. And now obviously we know C and we know D, so we can solve for A. Okay, so let's do that. So we get 0 is equal to A minus 9 over 4 plus 3. I'm going to multiply everything by 4. So I get 4A minus 9 plus 12. And so therefore A is equal to, so this is going to be plus 3. So I'll move that over here, get minus 3. So minus 3 divided by 4. And there we have it. Okay, so let's put those all into here. We have the A, B, C, D. So we get A times 1 over S plus B, it's 1 over 2, times 1 over S squared plus, it's actually minus 9 over 4 times 1 over, and I forget what that is, 1 over S plus 2. And finally, 3 times 1 over S plus 1. And look what we have here. So this is the particular solution from our technique before, and here is the complementary solution. So I don't know if you can see that yet, but I know this is 1, this is t, this is going to be e to the negative 2t, this is e to the negative t. So let's just write that out. So inverse Laplace transform gives us negative 3 over 4 times 1 plus 1 over 2 times t minus 9 over 4 e to the negative 2t plus 3 e to the negative t. Wonderful. So we got exactly the same thing. Let's just, I remember this particular solution, but let's just check the rest of it. Minus 9 over 4 plus 3. Precisely exactly the same thing. Okay, and just to kind of measure, I can fit the entire solution in this window here. And then if I do the same up here, yeah, I mean, it's about the same. I could almost fit this in, and I kind of write big. I could have made this smaller. So maybe it's about the same amount of writing. We have this kind of little bit more challenge finding this A here. So anyway, I like it though. I think the Laplace transform technique is quite nice. And the main thing that it involves is partial fractions. So if you like partial fractions, then you may like this. If you prefer partial fractions to taking derivatives and solving linear systems, then you're probably going to prefer this method. So I hope you get a lot of practice this a lot. Do a lot of examples, and I think you'll get the hang of it, and I think you'll like it. So next lecture, we'll go back to 4.1, and we'll actually look at the definition, and we'll actually derive some of these Laplace transform properties using the definition. So that's what we'll do next time. But now hopefully you motivated for like, why is the Laplace transform interesting? So there you go. Okay, so thanks for watching, and see you in the next lecture.